Well, welcome back for our examples for section 10.7. Again, we can use either root or ratio test kinds of concepts when building these intervals. In this case, we're probably going to go ahead and do the ratio, although the root test would work as well. So our C sub n in this case is going to be n over n plus 2. This is actually number 7 from the book. Notice we just have an x to the n, not an x minus a. In that case, a is 0. A series where a is 0 is often called a Maclaurin series, and we'll discuss that more when we look at 10.8. Okay, so we need to find this k, and k is going to be, again, the limit as n goes to infinity of either the nth root of c sub n, again, absolute value, or it's also equal to the limit as n approaches infinity, absolute value of c sub n plus 1 over c sub n. Notice you can use, again, either one of those is perfectly fine. Whichever one just looks best for that particular problem, go ahead and use it. But let's do some practice with the ratio. We've done some roots already. So I want to look at c sub n plus 1. That's going to be n plus 1 over n plus 3. So when I divide that by c sub n, okay, that means I'm going to invert and multiply when I divide fractions. N plus 1 over n plus 3 times, invert and multiply, n plus 2 over n. So we're looking at the limit as n approaches infinity of, let me see here, n squared plus 3n plus 2 over n squared plus 3n. It doesn't take a lot, just use L'Hopital's rule. 2n plus 3 over 2n plus 3, well, that is 1. Okay, so this thing's going to converge when x minus 0 is between negative 1 and 1, because notice our radius is 1 over this k, and this is k. So radius of convergence is 1 over k, which is still 1. So when x between negative 1 and positive 1, it's going to converge. Now, the question is, what happens when x equals 1 or x equals negative 1? Again, we said we have to check the endpoints because those are the ambiguous cases for root and ratio. Well, if x was equal to 1, we'd have the sum n equals 0 to infinity, n over n plus 2, because after all, 1 to the n is just 1. And these terms most certainly aren't going to 0, so that's going to diverge. When x is negative 1, you get the sum, n equals 0 to infinity. Well, it's going to be n times negative 1 to the n. And while it alternates, the terms are not going to 0, so we still get divergence. So our domain for this function defined by this series is going to be all the x values strictly between negative 1 and positive 1. Okay, let's try another one here. Again, let's take from the book number 11. Now, the minute I see a factorial, my clue is this is going to be a ratio. type of thing. You don't want to do with the roots of factorials. So again, we need to find c sub n is negative 1 to the n over n factorial. And again, in this one, a is 0. Okay, well, c sub n plus 1, that's going to be negative 1 to the n plus 1 over n plus 1 factorial. Now, one thing to remember is our factorial facts. Remember, n plus 1 factorial is multiplying n plus 1 times everything lower than it. So the next lowest number is n, and of course all the numbers lower than that. So one handy fact to remember factorial is n plus 1 factorial is simply n plus 1 times n factorial. That's going to be a commonly used relationship. So when I take and I divide these, c sub n plus 1 over c sub n, and I'll take the absolute value. So I'm not going to order the negative. Okay. So we get 1 over n plus 1. So k is going to be the limit as n goes to infinity of 1 over n plus 1 equals 0. Okay, this is that special case. Our radius is 1 over k. Well, obviously, if k is 0, it's not defined. So when k is 0, we interpret that as infinity. So my radius of convergence is infinity. In other words, this converges for all x. And obviously, there's no endpoints to check because, well, it's not a finite interval. Okay, so what we want to do next time is address the problem of if we want to have f of x to be the sum, and we have a sub n x minus a to the n equals 0 to infinity. Okay, we're defining functions this way. The question is, how can we find the a sub n's? And there's actually a nice formula for it. It's called Taylor's theorem. There are two people who developed this, Taylor and Maclaurin. So when a is 0, we always call it a Maclaurin series, and when a is not 0, it's called a Taylor series. So those two things really mean the same thing. It's just when it says Maclaurin, set a equal to 0. It's just a special case. But what we're going to get in the next section is simply a formula for a sub n. So it's really not a terribly bad section. Obviously, it's the way things are done when you're approximating. So if you wonder how does the sine function get computed by a calculator, it's using some type of a series. And obviously, it's going to have to round it off someplace. It turns out these a sub n's shrink fairly rapidly, in most cases. And so the terms get small real quick. And so if you add to the first term, you get a good approximation. Okay, so that ends our examples here for 10.7, and we'll hit the last section, which is Taylor's theorem, next time.